All right, you guys, so I believe this is where we left off. So we were talking about how we can use percent composition to be able to figure out how much of a compound is made out of each of the elements in it. And because we don't really write chemical formulas using percentages, we need to find a way to move from that percent composition into an actual chemical formula that we would traditionally see. So a formula of a compound is really just representing the ratio of the elements in that compound. And that's what allows us to move from the percentage, which is kind of like a ratio, into the formula. So if we consider styrene, it can help us understand the two types of formulas that exist. There's something called an empirical formula, which is the lowest whole number ratio of the elements in the compound. All ionic compounds are written as the empirical formula. They're always written as the simplest ratio. So ionic compounds are always an empirical formula. Molecular formulas, on the other hand, are the exact formula of a compound, or in this case, a molecule. So molecular formulas are more common when dealing with covalent bonds. You can see that styrene, that's a covalently bonded molecule. Styrene has an empirical formula, which is its simplest whole number ratio, which is C1H1, and it has a molecular formula of C8H8. Truthfully, the molecular formula is always the most meaningful. In the case of ionic compounds, the empirical formula and the molecular formula are really the same because you always write ionic compounds in the lowest whole number ratio. But the real difference comes when you start talking about covalent compounds. Sorry, this chair is so squeaky. Yeah. So if we want to figure out the chemical formula of a compound, and let's say we have our percent by mass. So we analyzed a sample and we calculated our percent compositions, just like we did in the first half of these notes. And we found out that the substance is 43.64% phosphorus and 56.36% oxygen by mass. So there's two objectives. The first one, part A, is to find the empirical formula. So let's find the simplest formula for this substance. Then we want to find the molecular formula. And in order to find the molecular formula, we have to know the molar mass. If we don't have a molar mass for comparison, there's really no way for us to determine the molecular formula. So part A plan, which is finding the empirical formula, goes like this. Step 1, assume there's 100 grams of sample. In this case, that would mean we would have 56.36 grams of oxygen and 43.64 grams of phosphorus. I used the percentages and the 100 grams of sample to calculate that we have 56.36 grams of oxygen and 43.64 grams of phosphorus. Because we're dealing with percentages, it doesn't really matter what mass of sample we assume because the proportion is going to be the same either way. But choosing 100 grams makes the math super easy because you can just turn the percentage directly into grams. You don't have to do any math. And if you don't believe me, you can work the math out and you will see that if you're assuming 100 grams of sample, this statement is true. So anyway, we have determined that there's 43 grams of phosphorus and 56-ish grams of oxygen. So now we want to use the molar mass of the respective elements to find the number of moles in each element. So for oxygen, 56.36 grams of oxygen, the molar mass of oxygen is 16. And so I'll use that molar mass on the bottom to cancel out the grams. to get my moles. So I have 3.52 moles. And then if I take a look at my phosphorus, molar mass of phosphorus is 30.97. So 43.64 divided by 30.97 gives us 1.4 moles of phosphorus. So this is handy. Now we have both substances in moles. And when both things are in moles, we can start to think about directly comparing them, because moles are moles, right? A mole of any substance is Avogadro's number of that substance. So moles are very comparable. Okay. Part 3 is that we're going to create ratios by dividing the mole amounts by the smallest mole value. So what I mean by that is for oxygen's mole amount, it's 3.52. Phosphorus is 1.41. So phosphorus is the smallest mole amount. That means that we will divide oxygen's mole amount by phosphorus's mole amount. 3.52 divided by 1.41, that gives us 2.5. We'll do the same thing for phosphorus, so it ends up being divided by itself. And so it gets a ratio amount of 1. And this is good because now we have our ratio of phosphorus to oxygen. However, we would never write the empirical formula as like P02.5, right? We would never say, oh, this molecule has 2.5 oxygens. That's not how atoms work. You can't have half of an oxygen atom. It's not oxygen anymore if you have that. So in this case, we want to multiply by a whole number, like 2 or 3, to try to make these a whole number. If you're way off base and you can't multiply by like 2 or 3 to make these whole numbers, you should probably double check your work, because typically you either get whole numbers out of your ratios or you get something that is clearly can be multiplied into a whole number. All right, so I'm going to multiply both of these ratios by 2. And so now I have that there's 5 oxygen to every 2 phosphorus. Those are both whole numbers, so we can use those in our formula. So the empirical formula for this molecule is P2O5. Now we got to move on to part B. Part B gives us the molar mass, 283.88 grams per mole, and it says, what's the molecular formula? So the molecular formula is always going to be some whole number multiple of the empirical formula. So we just need to figure out what that whole number multiple is. In order to do that, we have to calculate the molar mass for the empirical formula that we found in part A. So molar mass is equal to 2 times the mass of phosphorus from the periodic table plus 5 times the mass of oxygen. That should say 5 times 16, not 5 times 32. That's my bad, you guys. Sorry about that. And then that should give you 141.94 grams per mole. 141.94 grams per mole is correct. The 32 grams is not correct, but I put the right thing into the calculator. I don't know why I wrote the wrong thing on here. Anyway, okay, so now we have the molar mass of the empirical formula, and we can compare it to the molar mass of the molecular formula by creating a ratio. So we'll put the molecular mass on top because it should always be the larger value. And then we'll put the empirical mass, the smaller value, on the bottom. This is so we get a whole number and it's easy to figure out what to multiply the empirical formula by. So if I do 283.88 divided by 141.94, that gives me 2. So that means that the molecular formula is twice the empirical formula. The empirical formula was P2O5. So the molecular formula is P4O10. Okay, that's how we calculate empirical and molecular formula. Your turn. We've got 2 examples on here that you should work through to the best of your ability. I do have solutions as well, and I'll walk you through those. So please pause this, try this example, and then we'll talk about it. there is a key to kind of see if you're right as you go along. Here is the solution. So we have, this is really, I kind of wrote this in shorthand, but we have, so our chlorine was 71.65%. So I just directly converted that to a gram because I assumed 100 grams of substance. And so now I have 71.65 grams of chlorine. I divided that by the molar mass of chlorine to get that there are 2.02 moles of chlorine. Then I did the same thing with carbon, 24.27 grams of carbon divided by the molar mass of carbon, which is 12. That gave me 2.02 moles of carbon. Then I did hydrogen, 4.07 grams of hydrogen divided by 1.01 gives me 4.03 moles of hydrogen. So now I'm going to divide by the smallest value of moles. Both of these are the same, right? 2.02, 2.02, so it doesn't matter. So I divided 2.02 by 2.02 to get 1 for both chlorine and carbon. And then I divided 4.03 by 2.02 to get about 2 for hydrogen. So that gives me a molecular or an empirical formula, sorry about that, empirical formula of carbon, so CH2Cl. 1 carbon, 2 hydrogens, 1 chlorine. Next, to find the molecular formula, I am going to take the molar mass of my empirical formula. I'm going to calculate that. So it was 49.48, so 12 plus 1.01 plus 1.01 plus 35.45. Then I made my ratio. So I did my 98.98 molar mass divided by 49.48, and that gave me a ratio of 2. And so in this case, I need to double my empirical formula. C2H4Cl2 is my molecular formula. All right, second example for you. Go ahead and pause the video, try to work through this one. This throws it back to when we're looking at data, and so you're not given the percentages, you're actually given the raw data. So you're gonna have to go back and think about what's the best way for you to get a mole to mole ratio out of this. Okay, so think about how you want to do that and give it the old college try. I've got the solution for you on the next slide. Okay, so since this is giving us a mass of oxygen and the mass of the sample, the first thing that I am going to do is find the mass of the hydrogen. So up here where it says moles of hydrogen, to get to moles of hydrogen, I found the mass first. So I did the mass of the whole sample minus the mass of the oxygen, which told me there was 0.43 grams of hydrogen involved. Hydrogen's really tiny, so that's a reasonable number. Then I used the molar mass of hydrogen to convert it to moles, which gave me the same value because the mass of hydrogen is 1.01. I went on to do my moles of oxygen. So I took my grams of oxygen, 6.93 grams, divided by the mass of oxygen, the molar mass, which is 16. And that gave me 0.43 moles of oxygen, which is the same as my moles of hydrogen. So that tells me my ratio is 1:1. I appreciate that I used an equal sign here and a colon there. That's awesome. So our empirical formula is just HO, 1 hydrogen, 1 oxygen. Now we can find that molar mass, which is 17.01 grams per mole. And then we can compare that to the molar mass we're given, which is 34.0 grams per mole. We divide that out, we get a ratio of 2. And that tells me that my molecular formula is H2O2, which is hydrogen peroxide. I just realized sitting here that all my examples, the ratio between empirical and molecular is 2. That will not always be the case. Sometimes the ratio is 3 or 4. I apparently only picked examples that are 2, but there should be some on your worksheet that are more than 2. Thanks, guys.